system if you have another loadings other than sinusoidal force. Section 3. I think in this section, we would like to handle a special loading called unit impulse. And then we will introduce one very famous principle we call it the Hammer integral, which help you to handle very general situations. Firstly, what is unit impulse? Unit impulse, symbolically, we normally use this symbol, delta, to denote unit impulse force. Graphically, unit impulse force is something like this. We have a loading history. There is no loading right here, except a small durations. The duration of this, we call it unit impulse. The duration is equal to a small number, we call it epsilon. The height, the magnitude of this strip is 1 over epsilon. If epsilon is a small number, then you can see that the amplitude of this force is very, very large, 1 over a small number, a big number. When you integrate the whole loading along the whole time domain, you will get a number 1, a value 1. Integrations mean what? Integrations mean finding out the area of the graph, right? Find the area of this vertical strip, give you a value equal to 1. That's why we call that unit impulse. The area of the pulse is equal to 1, unit impulse force. This force is very important. This force gives us a very useful outcome later, because from this simple picture, some researchers found out some way to handle general loading, arbitrary loading. You will see that wonderful theory on the next slide. But at least we have to deal with this unit impulse force first. Suppose we have a single degree of freedom system under a unit impulse loading, not a psi function right now, it's a pulse loading, delta. We try to solve these equations. How to solve it? You can. I give you one picture to show you the displacement history. This is the displacement history. It's just like a sine or cosine oscillation from the graph here. We have seen this oscillation before in topic 5. Unit impulse response. By definition, not by definition, by solving the equation, we found that the unit impulse response, U, is equal to 1 over m omega d, the damped frequency, times exponential function, times psi something. How to solve this problem? Actually, this problem can be solved using the response of free variations. Response of free variations. Take a look on this picture. When you consider a time instant slightly after the unit impulse force, say for example here, if you consider a time instant slightly after the application of the loading, what is the value of loading right here? The loading is equal to 0. The loading is equal to 0. For structures under 0 force, then it belongs to free variations. We discussed already in topic 5. Topic 5. So you can recall the formula, the displacement for free variation in topic 5. We directly put it here. What you have to do is to you can see that the unit impulse force just like giving us some initial conditions. When a structure undergo free variations, to make it oscillate, you need two initial conditions: initial displacement or initial velocity. Initial displacement or initial velocity, so that the structure will oscillate under free variations. From this picture, the structure is initially at rest, no movement, so we have no initial displacement. So it seems that by rejection, the unit impulse force will give the structure some initial velocity, make it oscillate. How to calculate the initial velocity due to unit impulse force? You can use this impulse formula. By definition, impulse is equal to mass times velocity after the collisions minus mass times the velocity before the collisions, before the application of the impulse. This definition of impulse we learned in physics. Impulse is equal to 1 because unit impulse force. The velocity before applying the loading is equal to 0 because the structure is at rest before applying the loading. So by this simple calculation, you can see that initial velocity is equal to 1 over n, 1 over mass. It's just like physics. If you know initial displacement, if you know initial velocity, initial displacement is 0. Okay, you can put these two initial conditions back to the free vibration response. Then you will get this formula. Actually, we are using the concept in topic 5. You may go back to topic 5 and try to do this substitution yourself. Okay, you may prove this equation yourself using the free vibration response. Using these two initial conditions, then you will get this function. We call the H instead of U. Actually, you can call this U if you like, but this response is quite special. This response is quite special. So when you read the textbook, they give this response a special name called H, the unit impulse response function. But physically, it means our displacement function. It means our displacement function. But this response is quite special, so we give them a special symbol, H, rather than U. And you can see that when a structure is under a unit impulse force, it will oscillate up and down, back and forth, and then depends on the system. If you have damping, then the displacement will decrease as time goes on. If you consider undamped system, then it will keep oscillating forever. Okay? Unit impulse response. I mentioned several times that this one is important. Why this is important? A structure under a small pulse with area equal to 1. Why this result is important and useful? You may take a look on this picture. Suppose you have a structure under this loading. The loading P, this time it is not a sine wave, it is not a unit impulse, it's not a constant force. This loading is arbitrary, right? We have a curve, we have a peak here, we have a straight line, we have a sharp change. This loading is arbitrary. If I ask you to evaluate the response of a structure under this loading, and how to find the answer? We can apply the solution on the previous slide to find out the response of these structures under this arbitrary loading. How? As you can see from the picture, for this arbitrary loading, you can cut this arbitrary loading into many vertical strips. Strip 1, strip 2, strip 3, strip 4, and so on. For each strip, say for example, this highlighted strips. For these strips, it's just like impulse. It's just like impulse force. But the magnitude is not equal to 1. The magnitude is equal to the area under the curve. Okay? It's just like impulse here. It's just like one impulse. But the area is not equal to 1. The area is you have to calculate based on the graph. So mathematically, I assume that the width of each strip is equal to d tau. D tau is a small number. Talking about the width of the strip. The value of this line at any point is p tau. The force is a function of time. The time is called tau. So p times d tau gives you the area of the strip. Area of that strip. Time a delta function. Delta function is a unit impulse force. So this shows you the force function for our strip 1 or strip 2 or strip 3, depends on which time instant you're considering. For impulse 1, according to the previous page, we know the response, free vibration. You can use the same equation again by considering the second strip. The green one. We can keep applying this concept, calculate the response for all strips, and then add them up together. Say, for example, for strip 1, the response is equal to our unit impulse response, H, multiplied by the area of the strip. Because the impulse is not area 1, the area is equal to P delta tau. You can apply this equation n times. Depends on how many strips you have along the loading history. How to add up all the response together? How to add up response 1, response 2, response n together? Add up all the response mean doing the integrations. Integrate our response from time equal to 0 up to your target time instant t. So this is so-called the Duhamel integral. This one. The Duhamel integral means we consider unit impulse response, and then we divide the whole loading history to many vertical strips. We apply our unit impulse response n times. Finally, we add up all the response due to all impulse together using this integral form. If you know how to solve this integral, then you can find out the solution of that system under the arbitrary loading. The concept is pretty straightforward, just like superpositions. Okay, the concept just like superpositions, but you involve something like integrations. So theoretically, if you know how to solve this, for this integral, then you can find out the response for all kinds of loadings. Sine force, cosine force, impulse, or arbitrary loading, you can handle it if you know how to find out the result of this integral. But I can tell you that this the integration here is quite difficult to operate. Okay, so here I just give you some idea about what is so-called the Duhamel integral. I will not directly ask you to solve it. Okay, don't worry. I just give you the background. Because we may have some essay type questions, right? For essay type questions, I may ask you the physical background, what is so-called the Duhamel integral. But I will not ask you to solve it because it's not that easy. Right? I believe that is beyond the standard of undergraduate. But I think it's good to it's easy to understand. Just like superpositions. Add up all the results together, then you will get the total response. This idea is only true for linear system. If you play with linear structures, then you can use this Duhamel integral to find the total response in a theoretical manner. Later on in topic 7, I will introduce another techniques which can help you to handle arbitrary loading. I think that one is more common because that can be handled using computer software. In topic 7, you will learn how to use numerical method to handle arbitrary loading again. But at least this is a very classical theory, the Duhamel integral. So we spend a few minutes to talk about the background. It actually comes from unit impulse force. We cut our arbitrary loading to many impulses, apply our result n times, finally put them together, the Duhamel integrals. By using the Duhamel integral, you can find out the response for any excitations. These sections give you the results for our structures under step force and the rapid force, rapid excitations. Step force means this loading. We have a constant force applied suddenly on the structures up to with magnitude equal to P here. This force keeps forever horizontally. We call that step force. How to find out the result of a structures under step force? Well, you can use the Duhamel integral. If you're good in mathematics, you can substitute P equal to P0, a constant force, and then put it into the Duhamel integral. If you're good in math, then you can find out the result for these integrations. I mentioned that it's not easy because it involves exponential function, it involves a sine function. maybe is a little bit out of the scope of this module. So you can see that I turned this to reference because I'm not going to assess you too many mathematics. Just let you know the result. Suppose you have some time to deal with these integrations. Finally, you can get this displacement function. You may plot it using Excel, plot it using MATLAB or the other software. Then you can see that it will oscillate something like this. Just like a sine or cosine curve oscillations. The radiation amplitude decreases as time goes on. Snap force. Similarly, if you consider in other situations a Ramsey force, this force means a force is linearly increasing as time goes on, a straight line. The force can be represented using this equation, P0 times T over TR. You just pick one point here, measure the values, the time, it will give you the slope. And then using it, you can express the loading at any time instant mathematically. It becomes your force function. Similarly, you can solve for this response using the Hammett integral. Find out the integrations, then you can get the displacement solutions. Also, just serve as reference, let you know that the Hammett integral is quite general. You can handle it. You can use it to handle different kinds of loadings. A constant force, a Ramsey force, or sine force, cosine force, also okay. Again, for your information, if you like, you may go to the textbook to see more picture about the Hammett integral. Okay, now we know what is the Hammett integral. Then what next? Next, we would like to consider more realistic situations, a pulse excitations, a pulse. What is pulse? Pulse is a loading with short durations. So, for example, structures may under a half sideway pulse, rectangular pulse, or it may be a triangular pulse. A pulse means a loading appeared only for a certain period of time. Maybe I call this TD. After TD, the loading disappeared. We call this kind of loading as pulse excitations. The pulse shapes can be any shapes. It can be half sideway, rectangular shapes, or triangular shapes, or the other shapes, arbitrary shapes. How do I find out the result? If you're good in math, you can use the Hammett integral. Same solutions. You may solve it directly using classical method. Classical methods mean you treat this as a differential equation. Solve the differential equation yourself. Find out the particular solution, find out the homogeneous solutions. But sometimes you cannot get the result easily. If you want to solve the equation using classical method, solving the differential equation, the criteria is that you need to express the loading using some math function, sine function, cosine function, etc. If you cannot present the loading mathematically, then you can't solve it. Classical method, one possible solution, but not that easy. Testing your math skill. Method 2. Method 2, evaluate the result using the Hammett integral. The Hammett integral can handle any shapes of loading, but as mentioned before, you need to know how to find out the result of that integration, that complex integrations. So it seems that method 1 and method 2 is not that straightforward. Testing your math skills. Method 3. Method 3 using some idea called superpositions. Superposition is a very common technique for civil engineering applications. And then method 4. I highlighted method 4 because I only assessed your method 4 in this module. So I highlight this one in bold letter. I only asked you to understand how to use a very simple technique, approximate method, to find out the result of a system under pulse loading. But I will take some time to talk about method 3, at least let you know the background. But for assessment, I will only focus on the last one. The first one and the second one just for your information. I believe that the other module, Advanced Math, has already assessed you the skill how to solve differential equation. So I don't want to repeat how to solve differential equations. What about superpositions? I let you know the background. You don't need to use it. I just let you know the background, how to use superpositions to solve problems. I put a reference here. Suppose you would like to consider a square pulse, a rectangular pulse, a rectangular pulse. The pulse magnitude is equal to P0. The duration is Td. Beyond Td, the values drop to 0. So how to use superpositions? The idea is quite trivial. You may present a loading using two-step force. You can present the loading using two-step force equal to the scenario on the right-hand side. Loading 1, you have a constant step force applied along the whole time domain, apply forever. And then at time equal to Td, you apply an opposite step force, P2, with values equal to minus P0, apply on the other directions. So when you add up these two loading, it will become the original pattern. Okay? You can use this idea, superpositions, to find out the result of something. Firstly, find out the result due to the first step force, and then find out the result due to P2. Superimpose the result together, then you can get the result due to this rectangular pulse. This idea is called superpositions. So the idea is that if we have some standard solution, due to step force, due to a rapid force, due to maybe a sine wave, then you can superimpose the result together to get some simple shapes. Okay, this idea of superpositions. The basic idea is you have to get some basic solution first, and then you can play with those simple solutions to form different patterns. Not general, but at least there are some way how to use the existing outcome. This one is just for your information, not for assessment. Rectangular pulse, if you like, you may solve it mathematically. Here I show you the equations. If you're good in math, you can solve this equation. For this kind of rectangular pulse, you have to divide the loading into two time domains. For time smaller than Td, you have a force. For time beyond Td, you have no force. So when you solve it, you have to divide your equation into two scenarios to solve it, with force and without force. So if you solve it directly, you will get two expressions. Okay, you may solve it just solving a second-order homogeneous or non-homogeneous solution equations. Here I give you reference. You may solve it directly. Actually, I obtained directly from the textbook. The textbook gives you some standard solution for rectangular pulse, half sine wave, and also triangular pulse. But they are not that useful in our modules. This slide just shows you one concept again, dynamic magnification factor that we have seen in section 1 for our structures under a sinusoidal force. Right here, for our structures under a pulse, you can also borrow the concept, dynamic magnification factor, DMF, or you may call this RD. The concept is that even though you are under a pulse force, you can still able to define the ratio between the vibration amplitude to the corresponding static component. So using the same definition, you can also evaluate RD for different pulse shapes. The graph on the left-hand side just shows you different pulse durations versus the vibration period. The graph here we plot the graph of RD with different combinations for your reference. You can see that for different combination of loading durations to the relative vibration period, the result look quite different. For dynamic, we do not have a standard solution. So the solution is changed a lot for different parameters, quite different from static. Okay, I'll go back to something that we will assess you. Approximate analysis, this one I will probably assess you. When you want to consider a pulse, if you really want to find out the maximum displacement, then what you can do, here we introduce one approximate analysis method. You can roughly estimate the response displacement of a structures, provided that the pulse duration is short. How short is short? Suppose we are going to consider a pulse with duration shorter than 1/4 of the natural period of a structure. This is the criteria of using this approximate analysis. The pulse duration, TD. TD is the pulse duration. The pulse duration should be short. How short is short? TD should be lesser than this value, Tn over 4. Then why we call that short? The graph let you know a little bit about the background, the graph here. For different pulse, when you plot the RD over TD ratio, you can see that different pulse shape give you different curves. But at the beginning, when TD over Tn is a small number, at the beginning, the purple color region, you can see that the result for all pulse are similar. All curves are coincide along the same line, which means that in this region, it seems to us that in this region, the pulse shape does not affect too much our response. Okay, that's why for short pulse, we are allowed to use a general approximate idea to estimate the response of the structures, only for small pulse. Okay, because of the shaded area. So what about this method? This method is pretty easy. Firstly, you calculate the time integral of the pulse. The time integral of the pulse means the area, the pulse area. You can calculate the pulse area from the graph. You know how to calculate rectangular area. You know how to calculate half side wave. You know how to calculate this triangle. The area of this pulse is so-called the pulse magnitude, impulse of magnitude. These integrations mean area. Normally, I will give you the pulse with simple shapes. So you can evaluate the shape directly based on the graph. I give it a symbol I to represent the area of the pulse. Okay. And then the displacement, according to this approximate method, the displacement response is just like unit impulse response multiplied by pulse amplitude. Unit impulse response multiplied by the pulse amplitude, the pulse magnitude. The pulse magnitude means the area that we calculate on the previous slide. The area of the pulse times this psi function, something like that. This becomes our approximate displacement function for structures under a pulse force, regardless of the pulse shapes. The radiation amplitude, maximum deformation, is equal to the coefficient before the psi function. This gives you the maximum deformation of the structures. You may use it to check the diffraction limit, or you may use it to calculate the forces applied on the structures, so that you can plot the shear and moment diagrams for design purpose. The maximum equivalent static force is equal to stiffness times the maximum deformations. So approximate method, pretty straightforward. Give you one example to see how to use it. This example I prepared that using US unit. When you read the textbook, some textbook, quite a lot of textbooks, they written using US unit. The one that I give you, written by A.K. Chopper, they also written in US unit. So here I give you one example to let you know how to deal with this kind of situations. When you read textbook, at least you understand what they're doing. You may transform the unit back to SI unit if you like. Suppose there are structures, the height is 80 feet, 80 feet tall. The force shown right here. When you're written in US unit, the force is expressed using kilopounds, KIP, and time is universal. This is the pulse shapes, not something like a triangle. There are some properties, the weight, the stiffness. The stiffness is expressed using kilopounds per inch. Inch is also the unit of length. 1 foot equal to 12 inch. The period of the system is equal to 1.12 seconds. Theoretically, you can calculate period yourself because you know the weight, you know the stiffness, you know M and K, then you can calculate period yourself. But here, for demonstrations, I directly give the period. Damping ratio, 1.23%. So in this question, you are asked to find out the maximum base shear and maximum bending moment at the base level. But for this kind of dynamic problems, just like a little bit like a Sylvus method, we have to find out displacement first and then find out the corresponding forces. We have to find out the displacement first, like here. For structures under pulse, you can find out the displacement using approximate analysis. If you know displacement, you can evaluate the corresponding equivalent static force, which may help you to find out the moment and shear force at the base level. So go back to here. How to find out the displacement, maximum displacement of these structures? The structure is now under a pulse with these shapes. We just introduced one technique, approximate analysis. If you want to use approximate analysis, you have to make sure that the pulse is a short pulse. Short pulse means TD over TN should be less than 0.25. TD, from the picture, TD is equal to 0.08 second. TN is given 1.12. The ratio gives you a small number, 0.071, less than the limit. So it seems that you can apply this approximate method in your calculations. And then how to use the approximate method? You have to calculate the area of this pulse. You may cut this pulse into different strips. Here. You may cut this into different areas. You know how to calculate the area of triangle, trapezoidal, and so on. Right? So I think calculating the area of this part is not that difficult. 1, 2, 3, 4. You can calculate the area of these shapes. This is what I'm doing here. Calculate the area of this pulse loading. Suppose I do all the calculation properly, then I will get the area is equal to 1.2 kilopascals second. We know I. According to the formula before, according to the approximate method, maximum displacement is equal to the amplitude of the pulse divided by stiffness times 2 pi over period. It seems that we know all the parameters right now. We know the area of the pulse. We know K is given. We know we know the period. So by putting all the things together, the maximum displacement is equal to 0.821 inch. 0.821 inch. Stiffness. Here we can calculate equivalent static force. What is the idea of equivalent static force? The idea is that we consider the time instant at which the structure achieved the maximum displacement. At the time when the structure reached their maximum displacement, the corresponding equivalent static force, Fs0, can be calculated using the idea of stiffness. Displacement, time, stiffness give you force. At this stage, you may treat this structure as something like static. You freeze the structures at this time instant. The structure is now under one equivalent static force with value equal to 6.73 kilopascals at the roof level. Then what about the base shear? What about the moment? You may treat this as static problem at this time. Maybe equal to the loading force. Will be equal to the loading force, the loading Fs0, which is equal to 6.73. So this is a shear diagram. Moment is equal to force times the moment arm, 80 feet. We have to change feet to inch or change inch to feet. 1 feet equal to 12 inch. so you can do the conversion easily. This idea this question, we have two purposes. The first purpose just demonstrate how to calculate the pulse response using approximate analysis, just one simple equations. The pulse area, and then using the equation, then you can get the maximum displacement for pulse. Any shape. Second, introduce the idea, equivalent static force. You have seen this term before in section 1, I think, in section 1 of this part 4. For a dynamic problem, we firstly use dynamic equation, find out displacement, and then you can convert the problem back to static. Depends on what time instant you're considering. Here we consider the time instant when the structure reached the maximum displacement. And then you can calculate the corresponding force at this time instant, which is equal to K times the maximum displacement. After now, you can treat this as static. For a static, it's just like a cantilever column under a constant force, Fs0. You can evaluate the base shear, the base moment immediately. Just simple equilibriums. Moment equilibrium, force equilibrium. That's why we can, this idea how we can apply our dynamic solution to some force calculations, equivalent static. It's quite common, especially when you play with earthquake design. The last part I will not spend too much time because you can see that this part, periodic loading, is just for your reference. There are several references in this part. So when you review these notes, you have to read the title carefully. Periodic loading. Normally, I turn these to reference because of the complexity of the contents. These contents also involve quite a lot of mathematics, just like the Helm integral. So I prefer to turn these to reference. Yeah. Although the concept is not difficult, the concept based on Fourier series. Have you seen this term before? Fourier series. Or Fourier transform. According to Fourier series, any periodic loading can be described using summation of many harmonic components. That means, firstly, periodic loading means a loading with some repeated pattern. You can find out one repeating unit. By duplicating this repeating unit n time, you can represent the whole loading. We call it periodic loading. For all periodic loading, you can express them using many cosine, many sine components. This is based on so-called Fourier series by definitions. Loading equal to a constant plus cosine plus sine. We learned how to find out the response under a sine force. Cosine force, the response will look quite similar. Sine, cosine, they are quite similar, right? So you can superimpose all response together to get the final outcomes based on superpositions. This is the idea of Fourier series. To express the loading using Fourier series, you have to find out some coefficients. A0, AJ, BJ, this kind of coefficients. This line shows you the coefficients. You may find out the values. It involves some integration again. It involves some integrations. If you have time, you may try to play with these integrations by trying different periodic loadings. If you know the coefficients, then you can successfully represent the periodic loading using many cosine and many sine terms. At steady state, the steady state response, you may find out the individual response first and then superimpose all response together due to cosine, due to sine, due to constant force. Superimpose all the results together. It becomes the response to a periodic force, periodic loading. The concept is not difficult, but involve a lot of calculations. Involve the technique how to find out the coefficient A0, AJ, BJ, and also you have to take some time to find out the response for all components. So concept easy, but the calculation is quite complicated. That's why I also prefer to put it as something like reference. If you want to know more, you may have a look at the textbook. There's one reference example if you want to know how to use Fourier series. You may have a look of this example. Okay, but reference, I will not, that is not for assessment, just for the information to see how to use Fourier transform. If you want to know more, you may also have a look of this example. Just let you know how to calculate the coefficients and how to apply the result together. I plot a few graphs to show you the results. So in summary, in this chapter, topic 6, we introduce how to find out the response of structures under different dynamic forces. Firstly, we introduce structures under harmonic force. We discuss how to find out the steady state solution. We introduce one important factor, DMF, dynamic modification factor. And then there are several applications. Force transmission, radiation isolation, calculate damping ratio, and also accelerometer. And then we introduce how to play with impulsive loadings. You can use approximate method. And then we introduce one general idea called Duhem integral. And finally, we mention a little bit about periodic loading based on Fourier series. The principle is based on Fourier series. If you want to handle periodic loading, transform the loading to many sine, many cosine terms. Then finally, it becomes harmonic loading, many harmonic loadings. Just superimpose all the results together. These are all we are in this lengthy chapter, chapter 6, force derivations. End of chapter 6. Okay, we finally finished this long chapter, force derivations. Maybe we can have a short break at this moment. During the break, you may also open the file, tutorial 6. We will discuss tutorial 6 after the second break. Okay, let us go to our last part for the today lectures. The last part is tutorial number 6. This is tutorial number 6. This one is especially for harmonic excitations. You may download this document from Moodle. This is tutorial 6, number 6. We focus on harmonic excitations. What we learned in this part, harmonic excitations, we have a short recap about what we have learned in our notes. Firstly, we are dealing with a system, single degree of freedom system, under harmonic excitations. A side force, we use a side force as an example. The sinusoidal force can be due to machine, due to ground movement, or due to the other external effects. Machine is one classic example. When this machine operates, it will generate a downward force, making the structure move up, move down periodically. So you can model it using a sinusoidal force. After solving the differential equation, you can get the response of the structures in terms of displacement. There are two parts, transients and steady-state response. Basically, you can just focus on the steady-state response. The transient response is something not our interest. You can just focus on steady-state response, composed of 3 parts, UST, RD, and one oscillating function. We call it steady-state response. UST, RD, or the phase angle can be calculated using the equation at the bottom. This slide shows you the idea of response modification factor, RD. RD you can calculate using these equations. It's good to understand this picture, let you know how RD change at beta increase. We call the frequency response plot. In the notes, I also show you similar pictures with colors. At resonance, normally resonance mean beta approximately equal to 1. Frequency ratio is equal to 1. And then there are some special values for RD for the phase angle. In topic 6, we have a few applications. One application of harmonic vibrations is to evaluate damping ratio. Damping ratio means energy dissipation. For structures, you have different ways to dissipate energy due to crack, due to yielding, due to friction, due to heat, due to many mechanisms. There is no theoretical formula to calculate damping. So here we use another approach. We use our lab results to calculate damping of some of our structures. Estimate the damping coefficients using lab results. This slide shows overall what we have learned up to now to measure damping ratio of a system. In topic 5, we have learned 3 vibrations. Using 3 vibration response, you can use the logarithmic decrement equation to evaluate damping ratio using 3 vibration response. In topic 6, we have learned 2 methods. The first one is based on resonance amplification method. The second one is based on half power bandwidth method. They are using different lab results. 3 vibrations, you have to excite the structure, undergo 3 vibrations, measure displacement history, and then put them into these equations. Method 2 and method 3 are based on harmonic vibrations. So you have to, when you use the equation, you have to understand the situation properly. Depends on what data you have, whether you are doing the free vibration test or doing the harmonic vibration test. Don't use the wrong formula. And today we learned a new concept called force transmissions or vibration isolations. Force transmissions mean when the machine operates, it will transmit a force at the supporting level. Today, we have learned how to use transmissibility to find out the force transmitted to the structures using TR. Gravitational isolations mean when the ground under movement, this ground movement will transfer it to the structures, and then what the total acceleration field by the object. You can also calculate using total, transmissibility. So although they're talking about two different scenarios, but in terms of the formula, they are the same, using transmissibility. Question one, we we consider a machine supported by two steel beams. The mass of the machine is 545 kg. Suppose it is a machine. When this machine under operation, it will generate a vertical force, making the mass, making the beam moving up and down, up and down. A machine gives you some information. The machine operation frequency is 300 RPM, revolution per minute. And the machine loading is equal to, the amplitude of the loading is equal to 270. So simply speaking, this machine, when this machine operates, it will generate a force, PT. A sinusoidal force, PT is equal to the force amplitude time an oscillating function, sine omega bar t. This is how we express the force, a sinusoidal force. You know P0, you know the frequency, loading frequency, but you have to change the unit. The unit here is revolution per minute. Revolutions mean the rotation cycle, 300 cycle per minute. You have to convert the unit back to either hertz or radian per second. The mass of the machine of the setup is 500 something kilogram. Damping ratio is equal to 1%. The steel beam. For the steel beam, the elastic modulus is 205 GPa. The moment of inertia of one steel beam is for this number, this big number, and the length, total length is 2.4 meters. But the machine is located at the middle. So you know the geometry, you know the property of the loadings. What we're going to do. We are going to determine the displacement and acceleration amplitude at the midspan of the beam at steady state. So simply speaking, you can convert the problem to something like this. A beam, I draw in a 2D manner with a machine with mass at the middle. When the machine under operation, when it's operate, it will generate a force, a periodic force. You can measure, you can define the degrees of freedom at the middle. Okay, this is the problem. I give you some one or 2 minutes to think about how to deal with the problems. Later on, we will go to the solution together. We are now playing with a beam under dynamic loading. Actually, this one is equivalent to a ball and stick model. I give you some time to think about the solution, what you have to do, which equation to apply it. Then we can go to the solution together. The target is to evaluate displacement, acceleration, at steady state under sinusoidal force. So this problem is considering structures under sinusoidal force. We would like to know the response at steady state. In our notes, topic 6, part 1 or part 2, we have mentioned several times what will be the displacement at steady state. At steady state, the displacement can be expressed using this equation, UST times RD times sinusoidal force. This is the steady state displacement for our structure's single degree of freedom system under sinusoidal force. If you know displacement, this is displacement. If you know displacement, differentiate this equation twice. It will give you acceleration. So actually, this problem just asks you to apply this formula, U equal to UST RD psi something. You find out what is UST, find out what is RD, and that will be the displacement relative. Not that difficult. But normally when you play with this kind of problems, you have to convert your problem back to this something like a point and state model. We have to find out the corresponding mass, stiffness, and damping coefficients, MCK. These are the three fundamental thermodynamic properties for a single degree of freedom system. Mass normally easy because mass we use in this module undergraduate. You normally use non-mass in our problems. For non-mass, mass is mass. You just pick mass equal to 500 something. Mass is well divided, 545 kg. Damping coefficients. Damping coefficient C is something related to damping ratio. What is the relationship? Damping ratio equal to C over 2m omega n. So if you know damping ratio, normally you can calculate damping coefficients if necessary. So damping is also given in the problems. K, stiffness. Stiffness is the main problem in this problem. What is the stiffness for these structures? We are now talking about a beam under a loading and mid-span. We are talking about this scenario, a beam under loading and mid-span. What is the stiffness for this scenario? If you want to calculate stiffness of something, then you can treat this as something like a static problem first. A beam problem. If you're good in static calculation, you may use equilibrium or you may use energy principle to find out the relationship between force and displacement. The coefficient right here between the force P to displacement delta give you the idea of stiffness. You can use static to find out these coefficients. The value is equal to what? The value is equal to 48 EI of the beam over L quick. Okay, you can treat this as static. Apply a constant load at the middle and then find out the corresponding force displacement relationship. The factor is 48 EI over L quick. This gives you the stiffness of a beam under point load at mid-span. So the equivalent stiffness for this system is something like this. But there are two beams, beam 1 and beam 2. There are two beams for these structures. So you have to apply this stiffness twice, two beams, just like in parallel. And then you can evaluate omega n. If you know stiffness, then you can evaluate omega n. Omega n is equal to K over n. Natural frequency. If you know natural frequency, you can evaluate frequency ratio. Why we need to know frequency ratio? Because according to our formula, RD depends on only two numbers, damping ratio and frequency ratio. RD depends on these two numbers. Damping ratio is given 1%. So it seems that the last number is beta. Beta can be calculated right here. Just make sure the unit consistent to each other. UST, what is UST? UST by definition, UST is equal to the force amplitude over stiffness. P, you know it, P is 270. Stiffness at the bottom. Okay, so when you answer this problem, firstly, you can put down this steady state solution. Steady state solution. Then you fill in the blank, find out what is UST, find out what is RD. Then this is what you have to do for this example 1. There are many equations. You have to select the appropriate equations. Okay, these are the numerical numbers. When you consider a stiffness for a beam, simply supported beam under Pohnel and Misbach, the corresponding stiffness is equal to 48 EI L quick over L quick. Actually, you have learned different stiffness in this module. We have considered a frame structures under horizontal movement. We have two extreme assumptions, right? Rigid beam, flexible beam. You have also learned situations in which a cantilever beam under Pohnel and Misbach. In these questions, you consider a simply supported beam under Pohnel at the middle. So for different scenarios, you can apply different stiffness coefficients. For beam, simply supported beam under Pohnel and Misbach, the stiffness is equal to 48 EI over L quick. And then use this coefficient twice because you have two beams. You have two beams. According to the previous picture, 2 times 48 EI, this is E, this is I. They are given in the problems over the total length. Then you can get the total stiffness, 6 something, 6 times 10 to the power 6 Newton per meter. Here I use standard unit, Newton per meter. You may apply different units if you like. Some guy may let you use kilonewton. Some guy would like to use millimeter. Up to you. Stiffness. So we know what is stiffness. We know what is mass. You can calculate natural frequency if you like. But before calculating the frequency here, I would like to do unit conversions. According to the problems, the exciting frequency, omega bar, is equal to 300 revolution per minute. 300 revolution per minute. Revolutions mean cycle. We have a 300 cycle for 1 minute. Then what about per second? 300 over 60, 1 second, 1 minute, we have 60 seconds. So 300 divided by 60 give you revolution per second. 1 revolution, we have 2 pi radian. So 2 pi over 60 becomes your conversion unit. Convert the unit from revolution per minute to radian per second. Our standard unit for natural frequency, radian per second, 10 pi. 10 pi. Now you can evaluate natural frequency and then find out the frequency ratio. By definition, natural frequency equal to K of M. You know K, you know M, you can find out omega N. And then taking the ratio, you can find out frequency ratio. This is one useful parameter for a system under harmonic loadings, beta. Normally you need beta, no matter what scenario you are referring to. Beta is one important parameter for harmonic vibrations. Be careful about definitions. The excited frequency is on the top, natural frequency at the bottom. Do not reverse the order, otherwise you will get totally different results. Natural frequency, we have stiffness, we have mass, so you can calculate natural frequency, 100 something. Seems a big number. Frequency ratio, beta. Beta is equal to the exciting frequency over natural frequency, approximately 0.3. If you know beta, if you know damping ratio, then now you can calculate dynamic magnification factor, RD. There is a long formula for RD, right? Square root something. At steady state, our displacement response is equal to UST RD sine something. Differentiate this equation twice. D sine give you cosine, D cosine give you minus sine, and then you have to drag this omega bar out 2 times. So you have omega bar squared, sine something, okay? I group UST RD into one symbol called U0, just make the equation look slightly easier. So you have the equation for displacement, you have the equation for acceleration. These are the two things you are asked to evaluate in this problem. So finally, fill in the blank, find out what is UST, find out what is RD, then problem solved. RD depends on beta, depends on damping ratio. Beta is equal to 0.3, damping ratio is equal to 1%. Put the things into the equation. RD 1.1, UST Q over K, this small number. And yeah, simply do the multiplications. UST times RD. You have a small displacement at steady state. You may convert this to millimeter if you like. For displacement, we normally use millimeter in practice. But here I use meter. I did not do the conversions. Acceleration. Acceleration, we refer to the previous equations. UST times RD times omega bar squared. Around 0.049 meter per second squared. Okay, this is the answer for this example 1. How to apply our steady state displacement equation for beam problems. Some discussions. Once you know the displacement for these structures, you can evaluate the equivalent static force, Fs. Stiffness, you know it. Displacement, you just evaluate on the left-hand side of this problem. It becomes something like a static force applied at the middle of a beam. I believe that you can draw the moment diagram, shear diagram for these structures, and then you will know the maximum moment at this loading frequency. If you know the moment, you can check the capacity of the beam, steel beam. You know how to calculate moment capacity, right? What is the moment capacity of steel beam? Moment capacity, you may refer to steel design. Moment capacity is equal to, we call this MC, equal to design strength times the plastic modulus of the steel sections, okay? And if you know the capacity, if you know the moment due to dynamic loading, then you can do a comparison to see if there is any failure or not. Just let you know how to use the displacement further, not just knowing the diffraction. You can also use it to predict the moment, the shear force, something like that, using equivalent static concept. Example 2. Example 2 is not that straightforward if you just read the questions. Lengthy questions, maybe you have to have a look at the problem first to see what you are doing. Suppose we have a concrete bridge, girder. A concrete bridge is not a straight line because we have some curvature, we have some strain gauge, or we have crimping, making the bridge become something like a side wave. This is the shape of the bridge, not a straight line. We model the diffraction, the initial diffraction using this sine curve, and we assume that this initial diffraction, the amplitude is equal to 3.05 cm. This is the diffraction due to crimping, the bridge. Then what about these things? This thing is a car. A car, for simplicity, you can model a car using a spring mass system. We have a damper, we have stiffness. When this car moving from the left to the right, because the ground is not a straight line, when a car moving on this curve, the car will also oscillate up and down. Suppose the car is moving with a constant speed, V. Speed is 72.5 km per hour. In these questions, you are asked to determine the total deformation of the car, which means UT, total deformation of the car, UT. There are some different informations. The damping ratio of the car is 0.4. The mass of the car is 1,814 kg. The total stiffness is equal to this big number, 2.19 something. In this question, you're asked to find out total deformations of the vehicle. When it's moving along this curved bridge, it will oscillate up and down. What is the total deformation of this vehicle? The maximum value for sure. This problem, I give you 1 or 2 minutes to think about what to do. If you know what to do, if you pick up the correct formula, then this problem is highly easy. It's very easy. Otherwise, it will take you a long time to complete the calculations. I think we have only one equation related to total deformations up to now. You may go back to search which equation. There's only one equation, I think, related to total deformations in this chapter, topic 6. Now, if you directly solve this problem, I think it's difficult, right? Because it seems that it's quite different from the problem that we encountered before. We are talking about car here, something like machine and mechanical problems. But there's one trick to handle this problem. Now, the original problem is like this: the car is moving, right? The bridge is fixed, static. The car is moving. The bridge is fixed, static. You can change these two motions. You can keep the car fixed, but the ground moving. You can assume that the ground is now able to move, to shake, using a psi function. The ground shaking, I use UG. G mean ground, U mean displacement. The ground displacement can be modeled using a psi rate. You can transform the problem. The car moved, the ground fixed, to the opposite. The car fixed, the ground moved. Okay, you can transform the problem. They're equivalent, right? As long as the ground motion is able to reflect the motions. Then why I do these transformations? Why I make this change? Because in the previous sections, we have already considered this problem. How to find out the total displacement or acceleration of the car, of structures. We have seen similar thing before under the topic force transmission or vibration isolations. We have saw that problem before. Maybe I go to that page. Here. When the ground is moving due to ground acceleration or ground movement, the total acceleration or the total displacement is something related to transmissibility. Actually, in example 2, you're asked to evaluate the total displacement amplitude. ut. If you know TR, if you know UG0, then you can evaluate UT using transmissibility. So as mentioned, if you able to transform the problem to something like this, then this question is not that difficult if you can select a both equations. Otherwise, if you start from the first principle, it may take you a long time to finish the calculations. So what we're going to do, we would like to use transmissibility in our problems, TR. How to find out TR? TR depends on the two parameters, damping ratio and frequency ratio. So again, we are asked to find out these two numbers, damping ratio and frequency ratio. Damping ratio is given, fortunately. You know damping ratio. Then what about frequency ratio? By definition, frequency ratio is equal to the exciting frequency over the natural frequency of the system. Natural frequency depends on stiffness and mass. The good news is that in this problem, you know stiffness, you know mass. But it seems that you can evaluate natural frequency directly without difficulty. The difficult thing is about loading, because here we transform the problem to a ground movement. So you have to find out the corresponding expression for our ground movement functions. What I mean is here. You have to express the ground movement using this psi function. You have to find out what is UG0, what is psi, what is omega bar. Psi is not, it's nothing. You have to find out what is omega bar. UG0 is the amplitude of this psi curve. .05 cm. 3.05 cm. Then what about the loading frequency? That means the ground moving frequency, the ground shaking frequency. Omega bar. The shaking frequency is not that straightforward in this problem. Now, you can think about in this using this simple example. Suppose the car start from here, start from the left-hand side support, and then it will reach another support on the right-hand side. The distance is equal to 12.2 meters. Move from one support to the other support. When the car moves from one support to the other support, it is equivalent to the ground to complete one vibration cycle, right? One complete vibration cycle. So what is the time required from the car move from one point to another point? You know the distance, you know the speed. Distance over speed give you the time traveling from one point to another point. What is the physical meaning of this time? Time required to complete one vibration cycle. We call that period. We call it period. Period means time to complete one vibration cycle. I call this T bar because we are talking about the loading. The loading part. Frequency, omega bar, is equal to 2 pi over period. So you can use the speed of the car, you can use the distance between two supports to estimate the equivalent ground shaking frequency, omega bar. You can firstly calculate the period of the ground excitations, and then convert that to frequency, omega bar. If you know frequency, you can go back to the definition beta equal to here. Calculate beta. This is the background of this problem. We transform the problem to something like structure fixed ground movement, and then express the ground movement using a psi function. Try to evaluate the ground movement. Find out what is the amplitude, find out what is the frequency, omega bar. And then after that, you can use our transmissibility formula, find out TR. So here is some numbers. Suppose we convert our problem to a ground displacement function. The ground displacement function can be expressed using sine or cosine equivalent. Because in the notes, I'm using sine in the notes. So here I keep the content consistent. I use a sine function to model the ground movement. And then you have to evaluate what is the ground amplitude and then the loading frequency. The ground amplitude, 3.05 cm from the picture. The period, we find out period first, traveling from one support to another support. Distance over speed. You have to change the unit of speed a little bit because the speed is expressed using km per hour. km per hour. You have to change the unit to meter per second or some equivalent numbers. Meter per second here, I convert the speed to meter per second. And then the length over the speed gives you the time. The time means the period to complete one displacement cycle, 0.606 seconds. 2 pi over period gives you frequency, exciting frequency, omega bar, 10.36 radian per second. Natural frequency, by definition, we discussed this equation in topic 5, I think, few aberrations. Stiffness over mass give you natural frequency, and give you natural frequency. Finally, frequency ratio equal to beta omega bar over omega n. Frequency ratio quite close to 1. The frequency ratio is equal to 0.944. 0.944, quite close to 1. So what now? Now you can go to here, transmissibility. To calculate transmissibility, you use our damping ratio, you use our frequency ratio. Damping ratio is 0.4, according to the problems. 0.4, damping ratio. Beta, 0.9 something, 0.944. Then put them together, it becomes TR. TR. By definition, TR is equal to the total displacement of the structures of the ground over the ground displacement amplitude. So you just move the denominator to the left-hand side of the equation. TR times the ground displacement amplitude, which is 0. It will give you the total displacement of the vehicle, of the structures, which is equal to approximately equal to 5 cm, 5 cm. This is the total displacement of the vehicle, 5 cm. Okay, this is about the use of transmissibility of structures. Answer. Here one discussion, the last statement. Just like the example in the lecture notes, sometimes I will ask you to modify the system, make the performance better. Say, for example, try to suggest some methods to reduce total deformation of this curve. We have seen some of the problem today, right? In our lectures, we discussed the phase isolation problem, topic example 3 in the notes. How to improve the performance of the system. Normally, when you answer these kind of problems, I suggest you may take a look of what you have done before. How to calculate total deformations, UT. you use a simple multiplications, TR times the ground displacement amplitude. To reduce UT, it seems that you can reduce TR or reduce U0. But again, you cannot reduce UG0 because this is something that out of your control, unless you change the bridge. Otherwise, you have no way to change UG0. So it seems that the only chance is to decrease TR, make TR smaller, make TR smaller. If TR decrease, then UT decrease. That can fit the problems. How to reduce TR? When you just take a look at the equations, I think it's quite difficult for you to figure out how to reduce TR. So you can go back to the diagrams. This diagram I mentioned several times, they're quite useful because you can observe the property from this kind of graph easily. This graph I obtained from the lecture notes. In our current problem, the damping ratio is equal to 0.4. But again, we don't have the picture 0.4 for damping ratio. So I select the closer one. Maybe I use the graph, which is equal to 0.5. This graph damping ratio equal to 0.5. The shape of the line should be quite similar to our current situations. What is the frequency ratio for our problems? According to the previous part, it is something equal to 0.9444, something like that. That means recently we are located around this region. I change the color. Recently, our current position on the graph is here. Beta equal to 0.9 something, 0.944. So ask you the same questions. How to reduce TR? How to reduce TR? It seems that we have two chances to reduce TR. First, you may go left. You may go left, or you may go right. Increase beta or decrease beta can also help you to reduce TR. If TR decrease, UT decrease. Okay? This is how you can answer this kind of problem. You can have a look of this kind of graph. Then you can see which part you should refer to. You may decrease or you may increase. Adjust beta. You can increase the driving speed. You can increase the driving speed to make beta bigger. Increase the driving speed to make beta increase so that TR becomes a small number, especially if you have large beta. Or you may reduce the driving speed, then it may converge to a number like something like 1. The other way is to increase damping ratio. Increase damping ratio normally able to reduce the motion. Okay. So this is tutorial 6. We have 2 simple questions in tutorial 6. Today we complete all the contents in topic 6 about force derivations. We have considered harmonic force, pulse loading, and periodic loading. Next time we will continue our discussions in topic 7, numerical method, which is used to handle arbitrary loading. And last thing is that the quiz remain in the same day, week 10. So if you have no further questions, perhaps this is the end of this class. Thank you for joining this class physically or online. If you have no questions, we've come to the end of this module, of this class. Thank you, and see you next week. Bye-bye. Bye.